Okay, so welcome to the second day of the workshop. So the first talk of today would be given by Dr. Farhad Habib, who's in Boston. So this is the only online talk that is going to be there because unfortunately we couldn't get Farhad to come to India in this time. So Farhad actually did his PhD in biology from Ohio State, and following a postdoc at Kansas State, he actually joined University of Science Education and Research Pune as a faculty member, but subsequently moved over to industry. And right now, he's one of the leading figures in AI. And he was in Ikigai, but Farhad, your affiliation seems to have changed again, right? Emphasis.ai.
Yeah, recently I moved to Emphasis from Ikigai.
Okay, all right. So he's one of the leading authorities in artificial intelligence research, and it's with great pleasure that I invite Farhad to give this talk on the development of AI. So Farhad, over to you.
Okay. Thanks, Sitabra, for inviting me to give this talk. It's always a pleasure speaking at IMSC. I wish I could have been there, but well, just a minor correction. My PhD was in physics, not biology. So, well, with that. So in this talk, I'll talk about the development of AI. So essentially, I'll take you through the beginning of AI or machine learning to its not all the way to the current times, but to around neural networks, or where neural networks start becoming more prominent. And in the meantime, I'll also take you through a bit of code on how you can actually use machine learning in your own projects, how simple it is these days with the kind of frameworks that we have available, that you can try out different models. You can see the results reasonably quickly with not that much hassle. And in tomorrow's talk, I'll talk a lot more about the current major wave in AI, that is generative AI. So I'll talk about how, for example, models like, say, DALL-E work to generate images from text, or how models like, say, ChatGPT or other large language models generate their output, are trained, and so on. So today will be the more traditional side, traditional as in like around 10 years back. Tomorrow, we'll talk more about transformers and the generative AI wave. Okay, so with that, in today's talk, I'll briefly talk about one of the major things that often people ask is what is the difference between AI, machine learning, data science, and so on. So we'll briefly talk about that. Some of the early AI concepts, what makes AI, what is AI or machine learning, and what it is not. Then we'll talk a bit about things like linear models, decision trees. These are some of the more traditional approaches that were popular for machine learning and are still popular, and they have a lot of advantages. So I'll talk about them. We'll also go through some of a small notebook that I've made illustrating these models. And finally, we'll close with neural networks. So if it's possible, I would like it to be as interactive as possible. So in case I'm going too fast, or you would like to ask any question or something, feel free to stop me, and we can take it right then, or I'll pause every, say, 15-20 minutes. And if there are any questions, they can be clarified at that stage. Okay, so with that, what is the difference between AI, machine learning, and data science? So although all of these three things overlap considerably, and especially AI and ML are often used interchangeably, one of the differences between some of the major differences between them is one is in what is the main focus. So AI, or artificial intelligence, has a focus on simulating human intelligence in machines. So with AI, what we are trying to do is to try and build systems or models that essentially replicate what humans can do, or what another intelligent person can do. Machine learning tends to be a bit of a subset of AI, where you're essentially trying to train algorithms to make predictions based on decisions from data. Data science is a much more broader field, which aims to extract knowledge or insights from data. So data science is much more of a management kind of discipline, where you're trying to look at data in different ways and try to see what else you can extract from data, what kind of insights can come, and what can they inform about the kind of actions one should perform, and so on. So with that, let's move on. Okay. So machine learning can be broken into these major components. In my talk, I'll mainly focus on supervised learning. I'll almost not talk very much about reinforcement learning, which is a big part of machine learning, but we'll not go into this one for this talk. And then there is unsupervised learning. So supervised learning is everything where you have something to supervise your learning. So essentially, you have data and you have labels corresponding to that data. So for example, if you have a large number of images where each image has a label corresponding to it, for example, the label might correspond to what objects are there in the image, what are the locations of those objects, or it might be, for example, let's say you have tweets, and corresponding to every tweet, there is a sentiment associated with each tweet, and so on. So all those cases correspond to supervised learning. Some of the major use cases of supervised learning are in things like, say, fraud detection, image classification that I just talked about, things like weather forecasting, and so on. In unsupervised learning, on the other hand, we don't have we don't have labels associated with an image, labels associated with a data point. So it could be just unlabeled images, text as it is, and so on. So in unsupervised learning, oftentimes the goal is things like how to compress that data, for example, things like dimensionality reduction or clustering to find structure in the data without necessarily providing any kind of a priori structure to the data, and so on. And in reinforcement learning, the idea is that you allow the system to learn via making different kind of policy modifications. Policies could be how a particular system behaves given a particular state that it is in, and so on. So reinforcement learning is where things like, say, AlphaGo or those kind of models come into play, which have recently been used for example, playing chess or Go at a superhuman level. So these are the three broad categories of machine learning over here. So I'll briefly stop here if there are any questions. Otherwise, I'll go on to the next one. So here's a brief history of machine learning. So here you can see some of the kinds of models that and what time did they approximately come into play. So linear models are the simplest models. They have been around in various forms at least since 1800s. Linear models, while simple, are still very powerful and used in a lot of contexts and will continue to be used in many places. Neural networks are among the first times when things like artificial intelligence or machine intelligence came to be used. They started somewhere around the Second World War and are the mainstay of machine learning at this point, at least at the cutting edge, where we are using them for things like image recognition, voice recognition, transformers, and a host of other things. Then there are non-parametric models like k-nearest neighbors, clustering algorithms, and so on. Markov decision processes, these come around here starting around the 1950s. And the 1950s and 1960s was a particularly rich time for machine learning. And then around the 1970s and 80s was a period where what is called the AI winter set in, because all the expectations that and promises that were made for AI before then did not come to pass. So a lot of the expectations being unfulfilled led to a decline in funding and AI winter. And around 1990s is again where we started seeing AI being coming into its own. And right now we are in the sort of the renaissance period where there is a lot of funding, there is a lot of developments happening. There is a huge amount of change happening in AI in every different space that there is. Okay, so yeah, a little bit of math, not very much, but just be aware. Okay. So what is machine learning for? So very basic, in a very basic format, what we can say is that the common theme in machine learning is to solve a prediction problem. Okay. Okay, maybe that issue is solved. So I'll start speaking again. So in machine learning, the idea is that you give an input X and you predict an appropriate response Y. So for example, take a simple function. A function takes some input X and produces an output Y. And it could be any kind of function here. So it could be a function that takes in an image of an image and outputs what the image contains. So in this case, the first equation has a function of an image, and the output in this case is a cat. Or it could be another way around. For example, you could have a function that takes in a description of an image and outputs a corresponding image that fits the description. And these are both examples of machine learning. And we will see how both of these different kinds of functions can be built using different machine learning algorithms. Okay, so what are some examples of what AI can be used for or machine learning can be used for? So some of the more non-traditional examples are, for example, machine learning can be used to create images given a description. So you might have seen, like a couple of years back, this became very big. Models such as DALL-E came into force, and you could just provide a description of, say, something like a teddy bear skating in Times Square, and it would produce a very convincing image given the description. You could predict whether a tumor is benign or malignant from a radiology slide, or you could predict what is the next day's stock price. You could summarize an article, you could write an article, and so on. So, for example, here is an example of creating an image from a text prompt. And this was something that was thought fairly difficult to do, even as late as, say, 5 years back. But now it's regularly done. For example, somebody has given a prompt such as photo of a hip hop cow in a denim jacket recording a single in a studio, and you get a fairly good image with proper lighting effects and so on. The only difference here is that instead of a human, there's a cow. And this is an example of what is called generative AI, where the AI is generating something from given some kind of parameters. It could be used to summarize an article. So for example, I gave the Claude, the large language model from Anthropic, a small sentence. For example, machine learning algorithms are being used to explore vast chemical spaces and so on. And I asked it to condense the above paragraphs to 5 words. And it was able to do a fairly good job of it, even though it found, I mean, it used 6 words or 7 if you expand ML out. So it's good, but it's not perfect. But it did an amazingly decent job here. What is not ML? So some of the things that one of the things that is not machine learning is rule-based approaches. And rule-based approaches or expert systems were a major topic of research, I think, back in the 80s. These are highly labor intensive. They don't generalize very well. So the idea behind expert systems is you take an expert or a set of experts and you find out how they would do a particular task, and you try to teach the machine to do the task based on how experts do it. So you would ask them, like, how would you decide an image is, let's say, malignant or benign? And the expert might tell you that they look for these set of features to decide that, and you try and encode those features in a rule-based system, and that would be an expert model. So some of the issues with that are that it's very labor intensive. You need a lot of experts. It does not generalize very well. So the expert can learn, I mean, the expert can maybe teach what they know, but when newer kinds of data comes in or the data distribution changes, it does not generalize to that easily. And the models that come out of rule-based approaches are brittle. That is, they break down when the data is not conforming to what has been seen before by them. And we'll see again what brittle means in the context of different kinds of models as we go along. So in modern AI or machine learning, what we try to do is we don't try to deconstruct expert thinking. What we want to do is to let machine learning find its own way. So the idea, how does the machine learn on its own? So what we do is we provide large amounts of training data in the form of XY pairs. So X being the data and Y being the label corresponding to a particular data. And you give a large amount of data to the model, and you let the model learn. by learning, what we mean is the model tries to uh, change its parameters in such a way that the error between what it predicts and what is the expected prediction uh, becomes as less as possible. And that way, the model has learned uh, what the data is trying to teach. So the machine learning approach is something similar to this, that you take a large amount of data that we start from here at the top. Uh, and okay, we train a machine learning algorithm. We evaluate the solution from the algorithm. We look at the errors. Are the errors low enough? Are they within acceptable bounds that we have set for the problem at hand? And if they are, we can launch the model. If they're not, then we study the problem but a bit more, we train more, maybe change the kind of model, change the number of, change the hyperparameters for the model, and so on. And we keep doing this until our solution is good enough for the problem that we are using at hand. And once it is, we can launch the model. By launching the model, what I mean is that it can be used for further tasks where we have not seen the data. Okay, so when it goes wrong is when you get cases like this. For example, this is a case where the model was not trained enough, or maybe it wasn't able to generalize well enough. So it might have seen a few examples of what a football looks like, and it was deployed, and then this is what happens. Or it might have, I mean, the people who are training the model really focused only on footballs, but not on other objects that might look like footballs, which might also be present in a soccer field. And the AI camera was able to find a perfect or a reasonably good match to a football that it thought was a football. And this AI camera just followed the referee's head for 90 minutes of the game, completely, I mean, ignoring the reason why the camera was put into the match in the first place. Okay. The other cases where, for example, this is another example of overfitting, where you the model is trying to generalize from very small number of examples. In this case, it has only two examples, January and February, and it fits the rest of the months in the same pattern, even when, I mean, even when we know that it's not the case. So in this case, it's a case of lack of enough data to generalize. This is a more recent example, and this is what happens when models are deployed without enough guardrails in place. So this recently happened in Canada, where a person was chatting with the Air Canada chatbot, and the person was trying to get a refund, and he was able to convince the chatbot, as you might want to try to convince a human agent, and the chatbot agreed to a refund policy that did not actually exist in Air Canada's refund policies. And the case, I mean, Air Canada refused to honor it. The man filed a lawsuit, and eventually the court agreed that Air Canada should honor the refund policy that its chatbot put into place. And now other people are becoming more aware of the failures of, or the potential failures of large language models, where you have these gigantic trillion parameter models that can behave in ways that are fairly unexpected, even after a lot of training to try to get them to behave in a certain way. Okay. Okay, so before I start on some more concepts of machine learning, any questions at this point? Okay, so some of the key concepts that come across in machine learning, and we'll look over, are things like classification. Classification can be multi-class or binary classification. We'll also look at regression, what is a prediction function, what is training, and so on. So first part is inputs. What kind of inputs can a machine learning, can an algorithm take in? So the raw input type can be a range, can be a large number of types. For example, you can input text docs, you can input time series or images or sound recordings or DNA sequences and so on. And any of these inputs can be, it can potentially be analyzed. The part where the algorithms can only take in numbers, so it has to be converted in some form to numbers. So mapping a raw input to a set of numbers, rational numbers, let's say RD, is called feature extraction. And how you do feature extraction can be very important in terms of if you have better features, then you might have a much easier time on the training part. So a fair amount of attention goes into feature extraction or converting an input into a form that the algorithm or the machine learning algorithm can work with. So for example, here is an example of how a text input is converted to a set of numbers that can be used by a language model. So in this case, what I've done is I've given the script bits and scripts workshop on computational epigraphy and converted it to the set of numbers that ChatGPT would see. So here you can see that ChatGPT does not see it as these words. It breaks it down into different what are called tokens. And in this case, it has broken these down into 13 tokens. And you can see that the tokens are not exactly what you might expect, but they do make some level of sense. So one of the ways in which you might think about tokenizing text is, let's say you could take every character in text and convert it to an individual number. But what that does is it removes a lot of features of text itself. Like if every character is treated independently of the next character, then you lose the interrelationships between the characters in a piece of text. So you might think that I might move a bit higher and let's look at different words as features. But in that case, two different words, for example, bit and bits, can be fairly closely related, but they would still get entirely different features. And also, your feature space in that case becomes very large. So they came up with this this tokenization scheme where different subparts of a word can be mapped to a number. So in this case, we see that its is one token, which has a token ID 896, and has been given another token, which is 290, and so on. Another interesting part about this particular scheme is that words or letters that are very commonly used are given smaller numbers, whereas ones that are rarely used get much larger numbers. So for example, iGraph has number 45,920 because it's less likely to be encountered, whereas something like it's or and or on have very small numbers because they come much more frequently in a piece of text. Another part we'll see is that the order in which this might be written matters here. So for example, if I remove the first part where there is a colon, the exact same set of words, workshop on computational epigraphy, now gets a different set of tokens here. So you can see that workshop earlier was a single token, whereas now it's been divided into two different token, works and hop. And this makes it easier for the large language model to figure out how to process these tokens and so on. So this is how the computational or machine learning models end up making sense of what input is provided to them. So feature extraction, as I was saying, is a large part of trying to make it easier for the models to figure out what we're trying, the data that we are giving to them. And some of the techniques of feature extraction can be, for example, tokenizing text data or normalizing numerical values. This can be useful if, for example, you have an image and it has large number of different values and you want to bring them within a certain range, encoding categorical variables or extracting image features rather than giving a raw image, or aggregating transaction amounts, or log transforming numerical values when your values have a very large range, but let's say most of your data isn't at the extremes and so on. The next part is how do you evaluate a prediction? So for evaluating a prediction, what we do is we look at the loss function. The loss function is nothing but simply the difference between what is predicted and what is actual. And a better model will have a smaller loss than a worse model, other things being equal. So a loss function is scoring how far off a prediction is from the desired target output. And depending on the use case, you can have a range of different loss functions. Some of the more simpler loss functions are like mean squared error or mean absolute error, which are very frequently used. Some of the less commonly used functions can be things like contrastive loss or hinge loss, which are present in binary classification, or cross entropy loss, which is also present in binary classification, is particularly useful if you have unbalanced classes, and so on. Uh, so, okay, any questions here? Okay, so a bunch of points. At this point, we've defined what a model is, uh, what kind of inputs go into a model, and so on. A few points on before you begin modeling. So if you're looking at modeling, the first thing you do is you create a test set and a train set. Sometimes you don't create an explicit train and test set, but you might use k-fold cross-validation or something, or similar. So in a test train split, typically you might split the data into something similar to like an 80% training or a 20%, 80% training, 20% test set. We use the training set only for training and the test set for assessing performance. The 80-20 is not set in stone. You can vary that around depending on the size of your data set or other characteristics. One part that is important is that your train and test should have the same distribution. Otherwise, your entire modeling exercise is not, I mean, the values that you get out of your training and testing, out of your training exercise are not going to be reliable. So in some special cases, for example, if you're doing train test splitting with time series, you have to be careful around how do you do the train test split so that you're not, say, getting data from the future into your training data. So, for example, you could create a training set as a training set is everything before time t, a test set is everything after time t, and so on. But one part you have to be careful about is that there is no leakage of information from the future into the past. Another part you have to be careful about is that you're not using any features that leak information about the label into the features. And this can happen, for example, if, let's say, you're using the title of an image or the file name of an image as a part of your training data, and the file name of the image contains what the image is about. And these kind of things can happen innocuously at times. For example, you might use, let's say, a star rating as a feature when predicting sentiment of a product review. So in that case, it might happen that if you use star rating as a feature, the star rating is likely to be correlated to the sentiment. So if you're just trying to predict sentiment, that is not a good feature to have. In general, any kind of feature that you will not have during production time, or any kind of feature that will not be available to you at the time of prediction, should not be used in your data set. And as we just talked about in the last slide, in things like time series forecasting, using any kind of future data at any stage of data preprocessing should not be done. Otherwise, you'll end up with a poor model that, when you put it into production, will not do good. Some of the other things that you should be careful about are things like changes in data distribution. This is particularly important in many of the internet scale data sets where the data might be subtly drifting at all points in time. So for example, you might have seasonal changes. And in that case, for example, a model trained with a small data set, let's say in one season, may perform poorly when deployed in a different season. If your data was trained over a much longer period of time, let's say a few years, in that case, these kind of seasonal effects may or may not be present depending on what the data set is about. Things like economic shifts or demographic shifts. So demographic shifts can happen. Let's say if you train a model, and this is not uncommon, people do this. Like let's say you deploy a model for one particular country, the model works pretty well, and you move to another country and you try the same model. And it turns out that the model may not perform as you expected, depending on how different the two countries' demographics are. So demographic shifts can be detrimental to how good the model will perform. Things like technological advances, that's model trained on data from an older technology, may not perform well on data generated by new technology. And this is something that trips people up, even those who are experienced with models, that sometimes improvements in data quality can degrade the performance of a model. because the model has been trained on data that might be of poor quality. It has trained its, I mean, the weights and parameters have been set according to the poor quality data that it was working with earlier. And let's say the data coming in has improved. The older weights or the older parameters will, working with the new, better improved data, may actually produce a worse outcome. And you can see that how this can happen is, let's say you have a data set where there is a bias in the data in one direction. Now the model has corrected for that bias, and it's producing output that it can as best produce. Let's say a new data set comes in which doesn't have that bias, but it is fed to the same model which expects a bias. So in that case, even though the new data is better, less biased, the model performance will actually degrade. So any kind of data changes mean that the model will need to be retrained. User behavior changes. This is something that happens often, and especially when you're working in an environment where there might be competing products and so on. So models predicting user behavior can suffer when there are shifts in user behavior. Let's say a new social network comes out, then some users might shift to the newer network and things like that, which means that the older network will see changes in how the user in the data that in the distribution of the data that it is seeing. And last but not the least, you can have things like feedback loops. So feedback loops are the fact that deployment of models can itself change the data distribution. So this can be seen in models which are used to, for example, recommendation systems and so on. So if you have a movie recommendation system that recommends certain types of movies, then because those movies are getting recommended, people will start seeing those movies more. So the model is changing the data distribution by itself. And these kind of effects can be fairly subtle and hard to disambiguate from real changes in what the model should be predicting. Okay. Another thing that one should be careful about when building models is overfitting. So overfitting is a case where your where your model has poor generalization. So essentially, the simple thing is that your model is overfitting when your training performance is very good, but your test or validation performance is poor. So for example, if you look at the three graphs below, we can see that on the left, the model is not capturing the entire details of the data set. So it's underfit. In the middle, you have an optimal fit where we are seeing that the data is essentially around the dotted line and the errors are minimized. And in the last case, there is no error because the line is passing through every single point, but it is overfit because if a new data point comes in, it's very likely that the line would be completely off for the new data point. So that is overfitting. Okay, so now having gone beyond some of these concerns that you have before you start fitting, a few terms that we look at while fitting the data set. So while performing model training. So what are hyperparameters? So hyperparameters, parameters of a model are the weights of a model that are tuned as the model gets trained, while hyperparameters are parameters that you select about the model. So for example, hyperparameters may control things like model complexity or the type of model complexity. So for example, the number of trees in a random forest, that is a hyperparameter, or the number of predictor variables you might use in a linear model, that is a hyperparameter, or the number of layers and the size of layers in a neural network, those are hyperparameters. The kind of and any kind of thing that you select about a model is a hyperparameter, though the optimization algorithm used, the model type used, and so on. Okay. Okay, so we come to the basic machine learning workflow. So the way the basic machine learning workflow works is we start with the data set, we split the data set into training, validation, and test set. We repeat until we are happy on the validation set. So repeat this part until you're happy with the performance and validation set. That is, You do feature extraction, you choose a particular ML algorithm, you search for the best hyperparameters for the selected ML algorithm. So usually what you do is something like a grid search or some kind of an optimized search where you try to search for a set of different hyperparameters, which set of hyperparameters gives you the best performance. And then you evaluate the prediction function on the validation set. Finally, once you have selected a particular model, you can retrain the model on training and validation set. You evaluate performance on the test set finally, and that is the number that you report, and you can go ahead and deploy that model. So this is our basic machine learning workflow. Any questions at this point before I go with a linear model? Okay, so to start with, linear models are one of the simplest
Hello,
kinds
sir.
of models.
I have a
Yeah.
question. So my
Mhm.
question is related to overfitting, it leading to poor generalization. So
Mm.
I was wondering, since our main aim while optimizing our model is to get the line of best fit, and in
Mhm.
quest of that, at times we might get a linear, or at times it might be non-linear to fit, right? Based on the data distribution that we have. So, is it dependent on the data that we choose, or which one to be? I mean, what is responsible? Is it, I mean, how can we deal with it? Should we work on our model, I mean, the line of best fit that we found, or the data distribution? Because we have no control over the data, right?
Yeah, you don't have any control over the data. So your aim is not to get the best fit line for the data that you have. Your aim is that the model should have the best fit for data that you have not seen yet, which is what the test set represents, and which is what you wanted to represent. I mean, which is what you wanted to do for unseen data so far. So you can, if you fit very strongly to the data that you already have, but poorly to the data that has not been seen, that means your model is not generalizing. So the important thing that we want from a machine learning model is that it not only learns about the data that you're giving it, but also it learns about the data that it has not seen yet. And uh, so what we want it is to generalize from what it has seen. And a model that is overfitting is not generalizing well. It is fitting the data that's given to it very well, but not the data that it has not seen as yet. Uh,
So, isn't that what we are supposed to do? Because we need to minimize the loss function, right?
mhm.
So, and that we are supposed to do for the data we have, that is a training data. So, of course, the testing data will be a novel data, and what we have here is the test training data, for which we need to minimize the loss function.
You need to minimize the loss function for training as well as test data. So you don't want to just minimize for the training function while ignoring the test data, right? If you ignore the test data and just fit on the training data, then what you have is a model that is performing very well for the data that it has seen, but it's not working for the data that it has not seen. So for example, in this curve that is illustrated below, if you look at the last case where the curve is passing through every single data point, this data, I mean, this kind of a function would work very well for this particular set of points, but any new point that comes in would be wildly off. I mean, the error would be wildly off for any new data point that comes in.
Okay, sir. Thank you.
Any other questions there? Okay. Uh, So coming to linear models. So linear models, the simplest thing the thing that linear models do is minimize the difference between, I mean, all models do this, but the idea is that the linear model is linear in the coefficients of the variables that we have. In machine learning, we often add a regularization term, and the idea behind the regularization term is that it penalizes overfitting. So, for example, in this equation, what we see here is an L2 regularization, where what we have done is added, if you just look at the first term, in this case, h sub theta xi minus yi squared, what this is simply the squared sum of differences between the predicted and the actual. Now, what we have done here is we have added lambda with the sum of all the squared coefficients of the variables in this particular example. So what lambda controls is how large the coefficients can grow, because we are trying to minimize this entire term. If you put lambda equal to 0, which is equal to no regularization, essentially you get back the ordinary least squares equation. If you put a very large lambda, then you correspondingly shrink the coefficients, because you're penalizing any large coefficients with the regularization term that we have put in here. And some of the things that we can see is that if you try to put a L1 regularization, in L1 regularization, what you do is we are summing over the absolute values of the parameters, the parameter weights. So in that case, what happens is that it promotes sparsity. What happens in that case is that in case two features are contributing roughly equally to the model, then then having an L1 regularization would minimize one of the parameters to 0 while leaving the other one more or less untouched. So in that case, what happens is that a large number of parameters go to 0, which brings out a sparse model. And sparse models can be useful where, for example, your space or computation is limited at deployment time. In L2 regularization, which is the equation that is shown here, where we are squaring the weight. In that case, what happens is that if two parameters are contributing roughly equally to the output, then both of them would be equally reduced. So in that case, it improves the stability of the model. So the idea behind regularization is that you obtain a much more strong, a model that generalizes better compared to without regularization. So the overfitting is much less. I had a small notebook that we can use to see how easily one can perform hold on a second, where is my notebook? Okay, here it is. Are you still able to see my screen? I hope so. If you can't see my screen, or if you're still seeing the slide, I mean, you should be seeing a notebook here. If you're still seeing the slide, let me know.
Yeah, Farhad, we can see your screen.
As in the notebook.
As in the notebook, yeah.
Yeah, okay. So what we'll do here is I'll take you through a simple code that creates a random data set with 3 features, and we fit different kinds of models to it. And you can see how easy it is to change the model once you have a basic idea of what the process is like. So here, this is just a set of modules being imported. I'll run this part. What we do here is let's create a random data set with 3 features. So in this case, I've just created something random with 3 features. I'll call them feature 1, feature 2, feature 3, and a 4th target column. So they're created, and here we can look at the 3 features. So you can see it's a table with feature 1, feature 2, feature 3, and a target variable that is the 4th column over here. These are just random numbers within a certain range. It's nothing special about them. So we don't expect much of a correlation between them, but we'll see once what happens when you start fitting. Here, what I've done is we can plot the features against the target. So we can see feature 1 against the target. It's largely randomly distributed as expected. There is feature 2 versus the target, and feature 3 against the target. Now, as I said, we first perform a split against train and test. So I do a train test split. I've given the test size here as 0.2, which means that 20% test and 80% train. So let's go ahead and build a linear model. Once you have a data set, so any kind of data set that is in a tabular format like this, we can work with the kind of steps, the set of steps that I'm going to show you. So to start with, for linear model, we can import in Python, we can import from scikit-learn a linear model, and I've also imported ridge, so we can do a ridge regression, which is the L2 regression. And for the error, we are going to use mean squared error as over here. So we create a linear model. So essentially what we have is, I'll call it ridge underscore reg, and my regularization strength I've kept as 1. So here I've put alpha as 1. And this is the part that does all the heavy lifting. So essentially we do a dot fit and we give it what to fit against. So we've given X train, which is the features, and Y train, which is the label. And when you run that, it produces a fit, and it tells you and this part is the predictions and model evaluation. So we do a prediction against the test one. So we take the model, which we have just fit over here, the ridge underscore rect, and we predict it with X test. And here this calculates the mean squared error. And I run this and it says ridge not defined. Okay, what happened? Oh, I forgot to execute this one. So execute this. And I see that it produces a mean squared error of 2.09. And we can go ahead and do the best fit of the model that we created against all the 3 features that we have. And we can see that it has produced a reasonable fit against all of the 3 lines over here. So if you're ever looking to do a linear fit, all you need to do is you put your data set in a table like this, and then you can run a ridge regression with an appropriate alpha. We can try a different alpha, like let's say if we try a stronger alpha of 2, what happens to a mean squared error? So we can see that our mean squared error went up. So 1 was better than 2. We can also try, let's say, 0.5, and we might see that it is lower than before. So maybe this is better. Ideally, what we would do is to run it against a large number of them within a certain range to see what is the best regularization parameter to choose over here. Okay. Any questions about this part? Okay, if not, then I'll get back to the slide here.
Hello, sir. Just one quick question regarding this alpha value. So could you just explain again, how do we choose what value of alpha would be good for our model? And also, stronger alpha, does it imply more regularization?
Yeah, so stronger alpha does imply more regularization, and lower alpha means less regularization. 0 alpha would mean no regularization. How you choose that is by something, you could choose it by cross-validation. So essentially, what you do is you run a large number of training runs with different values of alpha, and you see for which values do you get the best or the least error for your particular data set. So what you want is that the error for the test set should be as low as possible.
Okay, sir.
Not the error for the training data set. So if you put regularization, in general, your error for the training data set will increase slightly, but your error for the test data set should reduce.
Also, sir,
balance between.
sorry to interrupt. You've been using this term cross-validation often. So, I mean, I know it, but could you just explain a little bit about that as well?
Okay, so cross-validation is, so I've been talking about the train test split, but what you can also do is just split your data set into a number of different sets. So let's say you can split it into 5 different data sets. And what you can do is you train against 4 data sets and use the 5th one as the test, then train against the other 4 and use the other 5th as the test, and so on. And then you average against all the test data sets to get an idea of what your overall error for that particular model is. So this is called K-fold, or in this particular example where I used, it's called 5-fold cross-validation. So the idea is that you don't have a single test and train set, but you are able to use your entire data set that you have to perform your training and evaluation.
Okay, so the error that the average error that we'll be having here will be the average of all the errors that we get during each fold.
So
Hi, sorry, I had one question for that. So
Mhm.
the question is, so this is like a frequentist approach, right? So you are doing this, this is sort of a chi-square minimization that we are doing here. So my question is that, does a Bayesian generalization of this kind of regularization exist? That is one point. And the second thing is, when you are doing the regularization, does this regularization algorithm take care of high covariances that might exist between the parameters in your model?
uh, high covariances would be so to answer your first question, yeah, Bayesian approaches do exist. In general, they're not very commonly used, partly because when you have a large amount of data, frequentist approaches just are easier to use. But Bayesian methods are there and are used. I'm not as familiar with them though. And the second question, um, could you repeat the second question?
Yes. So when you are doing this optimization, this regularization procedure, so the parameters that your model contains, now some of these parameters could be covariant. So when you are fitting,
They're correlated with each
yeah,
other.
exactly.
Yeah. So that's
So,
what I was trying to see. The regularization does take care of them in different ways. So, for example, if you're doing L1 regularization, if you have two correlated parameters, one of the parameters would likely go to zero and the other one will have all the weight. So you end up having a sparse model where one of the correlated variables does not have any weight at all. In case you're doing L2 regularization where you are minimizing the squared sum of the weights, in that case, both the weights would decline or decrease uh, roughly equally or proportionally. So in L2 regularization, again, your weights decrease. So it does take care of the correlations uh, to answer your question.
thank you.
Okay. Okay. Second class of, so I'll just describe a few of the methods. There is a very large number of machine learning algorithms, but some of the more popular ones. So in this one is called decision trees. So decision trees are particularly useful for classification kind of problems. And part of the appeal of decision trees is that they're very explainable, that you can tell exactly how you arrived at a particular decision. So for example, um, I'll go over the tree that you see here. But the idea behind decision trees is that they mimic human decision making. That is, your trees split data based on questions, resembling how humans make decisions. So the feature selection, what a decision tree does is it automatically selects informative features for splitting at each node. There is a bunch of ways in which it is done. Generally, the construction is a greedy sort of construction where uh, the decision, I mean, the split that uh, whatever metric we're using, for example, Gini impurity or entropy, whatever maximizes the metric is split at that point, and so on. So, for example, a decision tree that is shown over here is a decision tree for deciding what kind of animal it might be. So let's say you start at the root of the tree and ask the question, is the animal short or tall? And if it is short, then you can ask the question, does it squeak or not squeak? And the answer is it might be a rat or it might be a squirrel and so on. Now, in a real life case, what you would have is you have a large number of features and the tree splits the data set at every point, which depending on the feature that maximizes the metric that we are trying to that we are working with. So that's how decision trees work. The downside of decision trees is that they're fairly simple and in some ways highly explainable. But decision trees are very prone to overfitting simply because if you go deep enough in a decision tree, essentially every data point can become its own terminal node. And that way you can get like a perfect fit to every data point. But then the decision tree does not generalize very well. So to make decision trees more generalizable, various techniques have been made. One of the more popular ones is a bagging technique, which is called random forests. So what random forests does is a forest is a collection of trees, and the way these trees are generated is that you take a random number of features and a random subset of the data set itself to generate different trees. So when you have a large number of random subset of features and a random set of data, each tree might be prone to overfitting, but the collection of trees is very resistant to overfitting. So random forests combat overfittings because you're using multiple decision trees, each decision tree seeing only a subset of the data. The predictions are made by either majority vote during classification or by averaging during regression. And decision trees are highly parallelizable because each tree is being constructed independently. So it does make it easy to build decision trees on multiprocessing systems or GPUs as well. So let's say if we take the same data set that we had before and try to fit it using a random forest. So you'll see how once you have the basic framework down, how simple it is. So mainly all you need to do is from scikit-learn again, we import the random forest regressor. In this case, it's a regression problem. So I'm importing random forest regressor. Otherwise, I would have imported the random forest classifier. And we again create the model that is random forest regressor. And here I've put n estimators equal to 100, which means that create 100 trees. You could have you can again experiment with this as one of the hyperparameters. So you can create different numbers of trees if you like. And then this line does the fitting. So again, we give X train and Y train. This is our data and this is the labels, and we do a dot fit. And once you execute that, it creates a random fitted set of trees. And we can again plot how the fit looks like. And we can see that unlike a linear fit, which was straight lines, the random forest fit is fairly wavy line because it does not have to conform to a single forest. Each data point can be, as you move across different feature values, depending on which branch of the tree you're taking and how many trees are being considered, you can have a different set of trees. So random forests are actually one of my more favorite kinds of models. They work very well when you have a large number of categorical features and so on. So these models work pretty well across a fairly large range of use cases, especially when you have, let's say, a large number of categorical variables and some of the variables being very sparse and so on. Okay, any questions here? Okay, if not, then I'll go on to the last kind of models that I'll talk about today, which is neural networks. So neural networks are highly interesting and the mainstay of most of the research happening in machine learning today. So the origin of neural networks was that the neural networks try to mimic the human brain. So as we call them neural because they are sort of how it was thought neurons behave. But essentially, what we have is that they're composed of what is called layers of neurons, not to be confused with real neurons, because these are highly simplified, but they're called neurons. So a typical neural network has multiple layers. So what has been visualized here is like on the left, there is an input layer. On the right, there is an output layer. And any layers that are in between these input and output layers are called the hidden layers. And again, if you have a large number of hidden layers, large being 3 or greater, you can call it a deep neural network. But the important part is that neural networks are highly versatile. They are universal functional approximators. So essentially, any function can be approximated by a large enough neural network. The way in which neural networks are trained is that they essentially adjust weights based on errors to make predictions. And the applications of neural networks are fairly large. They can be used for image recognition, language processing, and a whole range of other tasks as well. And all the newer developments like transformers and so on are based on neural networks that we'll talk about tomorrow. And the interesting part, the major part to realize about neural networks is that the hidden layers enable the neural networks to learn complex patterns. So essentially, as you go deeper into a neural network, the different layers learn more abstract representations of the data that the input layer is seeing. So, for example, in this case, let's see. So what is a single neuron doing? So important, let's go a little bit deeper into a neural network. So what a neural network does is, if you look at a single neuron, which is the block represented by the Greek letter sigma here, is it takes in all the features that are arriving from the layer before it. So in this case, represented by x1 to xn, these are inputs. And the neural network has different weights corresponding to each of these inputs. So it multiplies the inputs by the weights. So we have the sum of all wi's with the xi's. Plus it adds a bias. So the bias is added as b over here, and sums them up and applies a activation function. The activation function is simply a nonlinearity, like a sigmoid or a ReLU. It has to be nonlinear. If it is linear, the neural network, the multiple layers of the neural network are not necessary, because if you add two linear functions together, you would get the same, you'd get another linear function. So essentially, if all your activation functions were linear, you could collapse your entire neural network layers into a single layer. So, so this is what a single neuron does. Now, the kind of activation functions that you can have there's a fairly large range of them, but these are some of the more popular ones. For example, sigmoid. Sigmoid is also popular for the last layer of a classification neural network, so that you can have a 0 or 1 output if you have binary classification. You can also have what is called softmax in case it's a multi-class classification. There are functions. The ReLU is a rectified linear unit. So a ReLU is a function that is zero below zero, that is flat below zero and equal to the x above zero. So it's a max of 0 or x. So essentially, you can see the main point is that all of these functions are linear. A different important part about different kinds of activation functions is that what the gradients of the neural of these functions are, especially when you move far away from 0. So in some kinds of activation functions, because the gradient is very low when it is away from 0, it can make training difficult, because the gradients are very low, so training becomes much more slower, and so on. Okay, so how do you train a neural network? So training a neural network is done by an algorithm called backpropagation. Conceptually, it's fairly simple, and even implementation-wise, it's not very complicated. So essentially, what backpropagation does is that you start with computing the difference between the actual and predicted outputs at the output end of a neural network. Then you calculate how what the gradient of each how the gradient affects the error using the derivative. So if you have the gradient and you have the error, you know in which direction do you move the weight so that the error is lowered. And you perform a slight weight update, that is, you adjust the weights to minimize the error based on these gradients. And you keep repeating this process from the output layer all the way to the input layer. And as you keep doing that, what you find is that the network converges to, the weights converge to a point where the error is as low as possible for the data set that we have. So that's how all neural networks are trained via the magic of backpropagation. We can again take the data set that we have and see how it does with neural networks. So again, in this case, what I've done is I'm using this framework called TensorFlow, which makes it easy to create a neural network. I'll create a small neural network with 3 layers. So my first layer is a dense layer of 64 neurons with an activation ReLU. My second layer is a dense layer with an activation ReLU again. And the last one is a dense layer with a single neuron because it's a regression task. And I am training it with an optimizer called ADAM, which stands for, I think, adaptive something. I'm forgetting that. And the loss we are going to measure is the mean squared error. So again, the line is the same as before. So we're doing a model.fit with our data and our labels. And again, so epochs indicates the number of times you want to run over a training data set to train it. And I put verbose equal to 1 so that it shows at each step what it is doing. So we can see here that it trained, because it's a small data set, it happened quickly. And we can see it started off with a large error. The error was around 4.12, and it keeps declining as it converges. And we can see that now that it's converged almost here, the next step, it was actually a bit larger than before. That's because this process is stochastic, a bit stochastic, it might have gone out of the minima. So once you've gone to the minima, it can just hang around the minima or like just sort of stay around there. And we can again fit and see what kind of fit do we see. And we see that with the neural network, the fit is quite different from what the kind of fit that we are seeing with a random forest, or somewhat similar to what we were seeing with a linear model. This was the linear model. This was the random forest, and this is the neural network. Okay, so that is about what I had for today. One part I do want to show you for neural networks is what you can experiment with yourself. So if you go to the site called TensorFlow Playground, what it allows you to do is to train different kinds of neural networks with different kinds of outputs and see what happens. So for example, let's say we have a data set here where you want to classify this. There are 2 kinds of data points. One type is marked in orange, the other one is marked in blue. And this tells you what kind of features do you want to feed in. So in this case, you have X1 and X2, which are labeled like this. This is X1, this is X2. We can choose the learning rate. We can choose the activation function between these 4 functions. We can choose regularization if you want to choose that, rate of regularization, and the type of classification problem type that we want. And there are a few other features as well. And let's see if we start training that, what happens. So we see that this is a simple problem and the network has converged fairly rapidly. I'll stop here. This part here, you can see that the test loss is now very, very low. The training loss is even lower, and the network trained very rapidly. If we choose a slightly more complex kind of output, let's say in this case, the classification boundary between the blue and orange points is slightly more complicated. Let us see in that case what happens. We can see that it's again able to do it. In this case, again, it's not super complicated. It took a little bit longer, but it was able to classify them very well. Let's see if we choose something a bit more complicated in which the orange and blue points are coming out together. So here we can see that the network takes a longer time to converge. So as you run, you see that initially the test loss had flattened out, and then suddenly the training loss has become much better, but the test loss is still fairly high. But the network is still trying. And maybe it's not doing, and we can see that it's stopped changing a whole lot. So what we can do is, let's say what happens if we increase the number of layers here. So you can increase the number of neurons, we can increase the number of layers. Let's say I've increased 3 hidden layers, 4 hidden layers, and then we try to do the same problem again. And it's a bit slower because the number of parameters is much larger now. But we can see that the training loss and test loss, it should be able to do much better now that we have a larger number of neurons. But one part I can say is you can play around with this particular, with different neural networks on this site, especially for a visual kind of data set. It shows, I mean, you can get an interesting idea of how different activation functions work, what is the effect of different learning rates, and so on. Okay, so I'll stop here. Any questions?
Hi, Farad. Nice talk. Yes, about this last example. So it looks like if you did some kind of nonlinear transform of the data, it would actually be a very simple problem to do. And so is the problem why the neural net is not able to get it something to do with the choice of activation function or the choice? I mean, is there a way to get a neural network to model some kind of a function using an appropriate architecture, or is it kind of an insoluble problem in this?
No, so you could, you're right that this problem would be much simpler if there was a transformation applied to the data set before it was fed to the neural network. In this particular case, the choice of properties that we have, for example, we can add more features, which is sort of indicating what you want to do with the neural network. I mean, what you want to do with the data before you feed it. So let's say if we add this, in this case, none of the features are particularly useful for the transformation that we might be looking at, but maybe sin x or sin x squared could help here. But in this case, the way this neural network is working, I don't think this transformation will happen. But like convolutional neural networks and so on will again not be useful for this classification task. So I think the transformation would have to be done in a way by hand. But if you could, I mean, if you apply that, then it becomes like a trivial problem. And
Thanks.
yeah, if it's also possible that given enough, like if you had some more, like I could experiment with this and see in case some neuron learns how to do it. But since you start off randomly, it's possible that the learning would help at some point be able to do it much better than what it is doing right now. Okay. I hope I was able to answer to some extent, Rahul.
Yeah, I don't have a good intuition for what these nets do, so I was wondering whether you had a better intuition. That's all. Yeah, thanks.
Any other questions? Yeah. So you said, I mean, during your talk, once you said that random forests are your favorite, right? So, so I was just wondering that do neural networks always perform better than random forests, or does it depend on the type of problem that you are dealing with? Some sort of quantification, some sort of optimization between which algorithm to choose?
No, they don't always perform better. Neural networks will always do better given a lot of training time. So oftentimes it's a difference of like things like how much compute or how much training time do you want to put in versus what you're expecting out of it. The part of the reason I said neural networks are my favorite is because I spent quite some time working on problems where there is a large number of categorical variables. And in those cases, neural networks do not tend to perform very well, particularly when the categorical variables might be largely sparse and so on. So in that case, a random forest does much better because it is able to, I think, fit the data. I mean, because you have a large number of trees, you can give like a huge number of trees, and some trees would do reasonably better. Whereas in a neural network, that led to a very large number of inputs, and the training was very slow. And for data points which are very sparse, the training would almost never happen at all. So I think that's the major reason I preferred random forests over neural networks for those kind of problems. For anything that is involving, say, image analysis or natural language processing and so on, neural networks would be the go-to choice. The one reason for learning and knowing about models that are simpler than, like, let's say you could throw transformers at every kind of problem, but things like it may not matter very much when you have small data sets or you're only doing a one-off inference of unknown data. But if you're doing inference all the time with very large scale and large scale number of queries coming in and so on, in that case, these kind of performance related questions become important, like how much compute are you using for every query that comes in. And you can see these kind of discussions sometimes happening around the profitability of many say companies like ChatGPT and so on, that every query is a few cents. If every query is a few cents, even if you were to say reduce it by half or something like that, you're saving millions of dollars every day. So it's a trade-off between things like training time, inference time, resources required to train, and so on.
Yeah, okay. Yes. Thank you.
Any other questions?
Hello, sir. So
Yes.
my question is, if I have a distribution at 0 to 1000 scale, but my data is distributed it mainly at 100 and 800 point, and very less data points are available in between. So will this approach be still useful, or should I go with the logarithmic distribution of the data?
I think for some of those kind of problems, I found random forest like approach is much more easier to work with because it sets different cutoffs. In that case, how you scale your data doesn't matter at all. If for any reason random forest is not working very well, then this kind of an approach could work well. A logarithmic transformation of the data set may or may not be appropriate. You would have to see how it looks like after doing the log transform. Log transforms are useful when, let's say, you have data that is going over a wide range, but it is naturally following a distribution that is in a way that log transform is capturing better. Like one reason log transforms are often used is many of the natural processes tend to produce distributions that are log normals. In that case, transforming the data by a log makes the data nicely distributed for further modeling. But if your data does not follow that kind of a distribution, a log may not be appropriate to use. I would say, like, just plot your data, do a log transform and plot it again and see whether, like, just eyeball it and see whether it looks better. And then you would be able to make a choice around whether or not that transformation is appropriate. Another thing to do is, if it is not very huge amount of data, is to do and feed both, like you can have both your log transform data as well as your actual data, and train a model and see, like, is it able to do better, and you can then look at the weights of the different features and see if the adding the log transform data is adding anything to your, is improving your result in any way. And you can leave both of them in. Like a lot of algorithms can, it may not hurt to add more features to you. That would be an example of an engineered feature. So it may not hurt to add more features to your data set, like different kinds of transformations. It may not,
Okay.
but it may not hurt.
Yeah. So in that case, the better approach would be compare different approaches.
Yeah.
Okay.
And you can also, so after you've done your fitting, you can perform things like what are called ablation studies, where you remove a feature to see whether your model is worsened. If it is worsened, then you leave it in. If it does not worsen, then that particular feature is unimportant and can be left out. So for the final model that you have, you can use a reduced set of features that like after you've removed all the features that didn't worsen your model performance when you removed them.
Okay, thank you, sir.
Mhm.
So if there are no further questions, let's thank Farhad once more.